There is a place beyond the last known planet where the light from our sun has faded to something barely brighter than starlight, where the temperature hovers just a few degrees above absolute zero, where the darkness is so complete, so ancient, and so vast that the human mind can only approach it slowly, the way your eyes adjust when you walk into a room where all the lights have been turned off. This is where we are going tonight. Neptune, the outermost of the 8 recognized planets, orbits our Sun at a distance of roughly 30 astronomical units, 30 times the distance from the Earth to the Sun, and even there, even at that extraordinary remove, even at a distance so great that sunlight takes more than 4 hours to arrive, we are still, in cosmic terms, close to home. We are still in the warm, well-lit neighborhood of our solar system. We are still, in a meaningful sense, inside something that feels familiar. But beyond Neptune, that is where familiarity ends. What lies out there, stretching from roughly 30 astronomical units to perhaps 10,000, is a realm that most people have never thought about, a realm that most scientists only began to seriously map within the last few decades, a realm that is still, even now, full of objects we have not yet seen, full of forces we do not yet fully understand, and full of mysteries so profound that they have the power to rewrite everything we thought we knew about how our solar system came to be. And one of those mysteries, perhaps the deepest and most unsettling of all, is that something out there appears to be pulling on the worlds we can see. Something massive. Something hidden. Something that, by all the mathematics we have, should not be unknown to us. But it is. And it has been, for a very long time. Let your breath slow for just a moment, because we are going somewhere remarkable tonight. The first region you encounter as you travel beyond Neptune is called the Kuiper Belt, a vast, donut-shaped reservoir of icy bodies that extends from roughly 30 to 50 astronomical units from the Sun. The name honors Gerard Kuiper, a Dutch-American astronomer who speculated in 1951 that the early solar system left behind a disk of primordial material beyond the orbit of Neptune. He was not entirely right in his reasoning, but the belt that bears his name is real, and it is extraordinary. The Kuiper Belt is home to hundreds of thousands of icy objects, ranging from small irregular chunks of frozen rock and carbon and silicate mineral to dwarf planets of genuinely impressive scale. Pluto lives here. Pluto, with its heart-shaped nitrogen glacier and its thin trembling atmosphere, which Mike Brown helped strip of its full planetary status in 2006 in one of the most famous and controversial acts of astronomical reclassification in modern history. Eris lives here too, slightly smaller than Pluto but in some measurements slightly more massive, orbiting on a highly inclined and elongated path that takes it far out into the cold dark. Makemake, Haumea, Quaoar, these are the inhabitants of the Kuiper Belt, ancient frozen worlds that formed in the early chaos of the solar system's birth and were then scattered outward by the gravitational jostling of the giant planets. But the Kuiper Belt is just the beginning of what lies beyond Neptune. Just the beginning. Beyond the classical Kuiper Belt there is a region called the scattered disk, and this is where the solar system begins to feel truly alien, truly boundless, truly unknowable. The scattered disk is not a neat, orderly belt. It is a diffuse, chaotic swarm of objects on wildly elongated orbits, objects whose paths take them swooping in toward Neptune and then hurling them back out again to distances that dwarf even the Kuiper Belt. Objects in the scattered disk can reach hundreds of astronomical units from the Sun at the far end of their orbits, and they move slowly, so slowly, at those distances, drifting through a darkness so complete that even the most powerful telescopes on Earth have only recently begun to detect them. And beyond the scattered disk, beyond even that, lies something called the Oort cloud, a vast, roughly spherical shell of frozen bodies that may extend to distances of 10,000, perhaps 50,000, perhaps even 100,000 astronomical units from the Sun. We have never directly observed the Oort cloud. we infer its existence from the long-period comets that occasionally fall into the inner solar system, these ancient wanderers that have been disturbed from their distant icy beds by the gravitational nudges of passing stars or the tidal forces of the galaxy itself. The Oort cloud is the outermost edge of our Sun's gravitational domain, and it is, by any reasonable measure, incomprehensibly far away. So here is what you should hold in your mind as you settle deeper into stillness tonight. Our solar system is not a small, tidy arrangement of 8 planets and a handful of moons. It is an enormous, structured wilderness, most of which lies in permanent cold and darkness, most of which we have only begun to explore, and most of which we understand only in the broadest mathematical strokes. And somewhere within that wilderness, at the outer edge of the scattered disk, at a distance that makes Neptune seem like a near neighbor, something appears to be hiding. How do we know? How can you know something is hiding if you cannot see it? This is perhaps the most beautiful part of science, the part that feels most like magic without being magic at all. You know something is there because of what you can see. You know something is there because the things you can observe are behaving in ways that only make sense if something else, something invisible, is shaping them from the darkness. Think of it this way. Imagine you are watching a group of boats on a river. Most of the boats drift with the current, moving more or less in the same direction, their paths determined by the flow of water beneath them. But then you notice a cluster of boats that are all tilting to one side, all angling toward the same distant shore. You cannot see what is pulling them. But you know something is. Perhaps there is a current you cannot see from where you stand. Perhaps there is something beneath the surface, some feature of the riverbed that is diverting the flow. The boats have told you, without words, that the river is not as simple as it looks. That is precisely what happened at the edge of our solar system. And the scientists who first truly understood what the boats were trying to say were a young theoretical astrophysicist named Konstantin Batygin, and a man who had already, once before, changed the way we understood our solar neighborhood. Mike Brown is, by any measure, one of the most important planetary scientists of the last 2 decades. He is the person who found Eris. He is the person who found Sedna, an extraordinary world in an orbit so elongated and remote that its discovery genuinely puzzled astronomers. He is the person who found so many large Kuiper Belt objects that he effectively made Pluto's demotion inevitable, earning himself the unofficial and only partly affectionate title of Pluto Killer. Mike Brown knows the outer solar system the way a cartographer knows a landscape he has spent his career surveying. He knows where things should be, and, crucially, he knows when something is wrong. Konstantin Batygin was, in 2016, a young faculty member at the California Institute of Technology, a theorist with a gift for orbital mechanics and a willingness to follow mathematics wherever it led, even if it led somewhere deeply uncomfortable. He and Brown were not looking for a new planet when they began the work that would change planetary science. They were trying to understand something puzzling that had already been noticed in the data, a whisper in the orbits of the most distant known objects that neither of them could quite explain. The story really begins with 6 specific objects, 6 extreme Kuiper Belt objects, sometimes called ETNOs, extreme trans-Neptunian objects, whose orbital characteristics had been quietly troubling astronomers for several years. These were not ordinary Kuiper Belt objects. These were objects on highly elongated orbits that carried them to extraordinary distances from the Sun, objects whose paths were, in the language of orbital mechanics, extreme, inclined, stretched, and strange. What Batygin and Brown noticed, when they laid these 6 orbits out side by side and looked at them carefully, was that they were clustered. Not in position, not in where the objects happened to be at any given moment, but in something more fundamental, the orientation of their orbits in space. To understand why this matters, you need to understand something about what an orbit actually is. An orbit is not just a path. It is a shape, and that shape has an orientation. It can be tilted at different angles, it can be stretched in different directions, it can point in different ways relative to the plane of the solar system. For the vast majority of objects in the outer solar system, these orientations are essentially random, scattered across every possible direction the way compass needles would be if you shook them up in a bag and let them fall. There is no reason for one orientation to be preferred over another. The solar system, at its largest scales, should be rotationally unbiased. But these 6 objects were not random. All 6 of them had their orbits oriented in the same direction in physical space, all of them pointing their most distant points, their aphelions, toward the same region of the sky. The probability of this happening by chance. Batygin and Brown calculated it carefully as they could given the constraints of the data they had, was approximately 0.007%. Less than 1 in 10,000. A statistical whisper so quiet that it could be dismissed as coincidence, but a statistical whisper that, when you truly listened to it, was screaming. Something was shaping those orbits. Something was, over billions of years, gently but persistently nudging these distant worlds into alignment, the way a careful hand might arrange a set of compass needles so they all point in the same direction. And for an object to exert that kind of gravitational shepherding influence over bodies at those distances, at hundreds of astronomical units from the Sun, it would need to be massive. It would need to be, by any reasonable calculation, a planet. Not a small planet. Not a Pluto-scale world. A planet of roughly 10 Earth masses, orbiting the Sun at somewhere between 400 and perhaps 1,000 astronomical units, on a highly elongated orbit that would take it far, far out into the cold dark before swinging back in again. A super-Earth, hiding at the very edge of the solar system, invisible to every telescope we had ever pointed at that region of the sky. The paper Batygin and Brown published in January 2016 landed in the planetary science community the way a stone lands in still water. The ripples went outward immediately, and they went far. The initial response was, as it is with any extraordinary claim, a mixture of genuine excitement and genuine skepticism, and the skepticism was entirely appropriate, because science without skepticism is not science at all, it is merely storytelling. The core objection was one of observational bias, and it was a serious objection, one that Batygin and Brown themselves acknowledged openly in their paper. The distant Kuiper Belt is not evenly surveyed. We do not look at it with equal attention in all directions. Survey telescopes tend to observe particular regions of sky, particular patches of darkness, and this means that the objects we have found may not be representative of the objects that are actually out there. If all 6 of your clustered objects were found by surveys that preferentially looked in the same region of sky, then the clustering you see in the data might simply be a reflection of where humans happen to point their telescopes, not a signal of a hidden planet. This was a legitimate concern. Batygin and Brown could not fully rule it out in 2016, and they said so. But they also pointed to something else in the data, something that the observational bias argument had a much harder time explaining. Among the known extreme trans-Neptunian objects, there were some that were not just aligned with the predicted direction of Planet 9's gravitational influence, but anti-aligned, orbiting in almost exactly the opposite direction. And the gravitational dynamics of a distant massive planet, when worked through carefully on a computer, actually predicted this. A planet orbiting in one direction will not just shepherd nearby objects into alignment with itself. It will also, through a mechanism called mean motion resonance and secular orbital coupling, force some objects into a perpendicular or even anti-aligned orientation. The anti-aligned objects were not a problem for the Planet 9 hypothesis. They were confirmation of it. There was also the question of objects with highly inclined orbits, bodies that circle the Sun on paths nearly perpendicular to the plane of the solar system. These objects had always been mysterious. Nothing in the standard model of solar system formation predicted them easily. But the gravitational influence of a planet at the distance and mass Batygin and Brown were proposing would naturally kick some scattered disk objects into these polar orbits over millions of years, sweeping them upward like a hand tilting a spinning top. This was an additional, independent prediction of the Planet 9 hypothesis, and when astronomers went back and looked at the data, the high-inclination objects were there, sitting quietly in the archives, waiting to be recognized. And Mike Brown. Mike Brown, who had spent years hunting the outer solar system and who knew better than almost anyone how easy it is to be fooled by incomplete data. Mike Brown took this seriously. Not because he was certain. Not because he believed with the fervor of a convert. But because the mathematics was clean. The mathematics was honest. The mathematics was saying something that deserved to be listened to, and Mike Brown, whatever else you might say about him, has always been a man who listens to what the mathematics says. He and Batygin went back to their computers. They ran the simulations again and again, varying the assumed mass and distance and orbital parameters of the hypothetical planet, checking what each scenario predicted against what was actually observed in the data. The predictions kept matching. Not perfectly, not with the precision of a laboratory measurement, but consistently, persistently, in the way that a genuine signal matches even when you look at it from different angles and with different tools. It had the feel of something real. The planet they were predicting was unlike anything in our solar system. A world of 10 Earth masses is what astronomers call a super-Earth, the most common type of planet found orbiting other stars but, puzzlingly, absent from our own solar system's inner and middle regions. It would be, if it exists, a world with a thick, extended atmosphere of hydrogen and helium, perhaps with a rocky or icy core beneath, perhaps with surface conditions so extreme that no human frame of reference could meaningfully describe them. And it would be so far away, so impossibly remote, that the Sun, seen from its surface, would appear as nothing more than the brightest star in the sky, a cold, distant point of light, barely warming anything at all. The question of how such a world ended up there, at such an absurd distance from the Sun, was and remains one of the most interesting unsolved puzzles in the entire story of Planet 9. Our solar system's giant planets, Jupiter and Saturn and Uranus and Neptune, formed relatively close to the Sun and then migrated outward over millions of years through a process of gravitational interaction with the disk of gas and dust that surrounded the young Sun. But a planet at 500 or 700 astronomical units would be so far from that disk, so far from the reservoir of material that fueled the giant's growth, that it is very difficult to understand how it could have formed there in the first place. The more likely explanation is that it formed closer in and was then ejected outward, flung to the solar system's edge by a close encounter with Jupiter or Saturn during the chaotic early period of planetary migration. Computer simulations suggest this kind of ejection happens reasonably often in the history of solar systems. Most ejected planets are sent flying into interstellar space entirely, becoming the rogue planets that drift between the stars. But occasionally, just occasionally, a planet is ejected into an extremely elliptical bound orbit, not quite free of the Sun's gravity, tethered to it by the thinnest gravitational thread, condemned to wander the cold outer dark for billions of years. If Planet 9 exists, that may be its story. A world that was once perhaps a neighbor of the gas giants, warm enough in relative terms, active enough perhaps to hold interesting chemistry, but then caught in the gravitational crossfire of the early solar system's rearrangements and thrown outward, far outward, to a place so remote that even the passage of billions of years has not been enough to bring it back within the reach of our instruments. There is something profoundly moving about that image, if you let yourself sit with it for a moment. A world, perhaps the size of twice or 3 times the Earth, orbiting alone in the dark at the very edge of everything we call our solar system, its origin perhaps as violent and chaotic as any planet's, its current existence as cold and still and silent as anything in the universe. And we have not yet seen it. We have not yet confirmed it. But the mathematics keeps pointing at the same region of sky, the same orbital arc, the same dark corner of the solar system, and saying, quietly and insistently, something is there. Something is there. And the journey to find it, and the complications and contradictions and deepening mysteries that have followed in the years since Batygin and Brown published their paper, is the story we are going to spend tonight unfolding together. But before we go further into the evidence and the searches and the extraordinary new data that has arrived in 2026 from instruments that simply did not exist a decade ago, before we go into the black holes and the modified gravity theories and the debates that have filled the journals and the conference rooms and the late-night conversations of planetary scientists around the world, let us just rest for a moment in what we have already established. Beyond Neptune, in a darkness so complete that it makes our most remote explored territory feel like a well-lit room, there is a vast and largely unmapped wilderness of icy worlds. And among the most distant of those worlds, the ones on the most extreme orbits, there is a pattern in the data. A clustering. An alignment. A signal in the mathematics that, when you follow it carefully and honestly, leads to a single, extraordinary, uncomfortable conclusion. There may be a planet out there that we have never seen. A world of 10 Earths, orbiting our own sun, unknown to us not because it is new or because it arrived from somewhere else, but because it has always been there, in the dark, at distances so extreme that our instruments have only recently become capable of even beginning to search for it properly. This is not science fiction. This is not speculation disconnected from evidence. This is where the data leads. Imperfectly. Uncertainly. But persistently. And the people who have followed that data, the astronomers and theorists who have spent years searching the outermost reaches of our solar neighborhood with the largest and most sensitive instruments ever built, are, as of tonight, closer to an answer than they have ever been. But they do not have the answer yet. And that uncertainty, that beautiful, humbling, slightly terrifying uncertainty, is exactly where we are going to live for the next several hours as you drift, slowly and gently, towards sleep. Let the darkness settle around you. Let your breathing slow. Let the sense of scale and distance and cold and silence wash over you like a wave, because that scale and distance and cold and silence is real. It is out there right now, surrounding us, the vast majority of the solar system's volume, an empty dark ocean that we have barely begun to navigate. And somewhere in that ocean, if the mathematics is right, something is waiting to be found. Something that has been waiting, perhaps, for as long as the solar system has existed. Something that was there before the first single-celled organisms arose in Earth's ancient seas, before the Earth itself existed at all, before the Sun ignited, in the long slow gravitational collapse that formed the disk of gas and dust from which all of this, all of us, eventually came. A world older than life. A world colder than almost anything. A world at the edge of everything we know. That is where we are going tonight. Breathe slowly, and let us begin. The way science actually works, the real texture of it, is nothing like the clean narrative we tell afterward. It is not a straight line from ignorance to knowledge. It is a long, difficult, sometimes maddening process of noticing things that are slightly wrong, of following small anomalies through years of careful work, of arguing with colleagues and checking calculations and waking up at 3 in the morning wondering if you have made a fundamental error somewhere, of publishing results that feel both exciting and uncertain and then watching the community pick them apart from every angle imaginable. This is what Batygin and Brown lived through in the years after their 2016 paper, and it is, in its way, as interesting as the science itself. The initial flood of media attention was extraordinary. The paper was covered everywhere, not just in the scientific press but in newspapers and magazines and on television, because the idea of an undiscovered planet in our own solar system, hiding in plain sight for billions of years, touches something deep in the human imagination. We thought we knew our neighborhood. It turns out we may not. That is a story that needs no embellishment, no dramatic framing, because the drama is already there in the data. But alongside the excitement came the technical objections, and the technical objections were worth taking seriously. The observational bias argument, which we touched on earlier, was pushed forward most forcefully by a team of researchers who argued that the apparent clustering of extreme trans-Neptunian objects was not a gravitational signal at all but a survey artifact, a consequence of the fact that most of the searches that had found these objects had been conducted in similar regions of sky at similar times of year. If you only look in certain directions, you will only find things in those directions, and those things will naturally appear to cluster in the direction you are looking, regardless of whether any gravitational body is doing the shepherding. This is not a trivial objection. It is exactly the kind of systematic error that has fooled astronomers before, the kind of thing that careful science has to take seriously. Batygin and Brown fought back against this objection with what data they had. They pointed out that several of the most compelling clustered objects had been found by surveys that looked broadly at the sky, not narrowly at a single region. They argued that a pure observational bias explanation struggled to account for the anti-aligned objects and the high-inclination objects, which were independent predictions of the Planet 9 model that had been borne out. They ran statistical analyses in which they tried to simulate what the observed distribution of extreme trans-Neptunian objects would look like under different models of survey bias, and they concluded that even accounting for the biases they could quantify, the clustering remained significant. Not overwhelmingly significant. Not beyond all possible doubt. But significant enough to take seriously, significant enough to justify continued searching, significant enough that the null hypothesis, the idea that nothing unusual was happening, was harder to defend than it looked at first glance. The community remained divided. It still is, to some degree. But in science, division is not failure. Division is the mechanism by which better data is demanded, by which the question is refined from "does this exist" to what evidence would conclusively answer that question, and that refinement is exactly what happened in the years following 2016. Teens around the world pointed their telescopes at the outer solar system with new urgency, new focus, new purpose. The Subaru telescope in Hawaii, the Dark Energy Survey, various dedicated sky surveys. All of them looking for more extreme trans-Neptunian objects, looking for more data points that could either strengthen or weaken the statistical case, and most importantly, looking directly for the planet itself in the vast dark region of sky where the mathematics said it should be. They did not find it. But they found other things. Things that complicated the picture in interesting ways, things that raised new questions even as they partially answered old ones, things that made the outer solar system feel even stranger and richer and more full of unexplained structure than anyone had appreciated before Batygin and Brown pointed at it and said, "Something is wrong here." We will come to all of that, the failed searches and what they ruled out and what they left open, the new objects discovered on orbits that fit and orbits that don't quite fit, the extraordinary capabilities of the instruments that have come online in the years since 2016. we will come to the remarkable and still unfolding story of what the James Webb Space Telescope and the Vera Rubin Observatory, the most powerful survey machine in the history of astronomy, have added to this picture in the most recent data. But for now, for this moment, as your body settles and your thoughts drift and the world outside becomes quieter and more distant, just hold the essential shape of what we have established. There is a mathematical signal in the orbits of the most distant known objects in our solar system. That signal is either telling us something real about an unseen world, or it is a product of our own observational limitations, a ghost created by the way we have looked at the sky rather than something actually there. Distinguishing between these two possibilities has been one of the central challenges of planetary science for nearly a decade. And the tools we now have to address that challenge are more powerful than anything the scientists who started this investigation could have imagined. The James Webb Space Telescope, floating 1 million miles from Earth at the second Lagrange point, staring at the deep sky with infrared eyes of unprecedented sensitivity, has been turned toward the outer solar system in ways that were not part of its original mandate but that have become, as the Planet 9 mystery has deepened, some of the most scientifically compelling work it has done. What it has found, and what it has not found, and what the combination of those findings means for the question of whether a 9th planet orbits our Sun, that is the heart of where this story is going. And the Vera Rubin Observatory in Chile, which began its legacy survey of space and time in the early years of this decade, sweeping the entire visible sky repeatedly with a camera so large and sensitive that it will ultimately produce a map of billions of objects, hundreds of millions of galaxies, and, critically, tens of thousands of new solar system bodies that no one has seen before. The Vera Rubin Observatory is already changing what we know. Its early data releases have been, depending on who you ask, simultaneously exciting and confounding, the way the best discoveries always are. All of that is ahead of us tonight. For now, let the darkness settle. Let the scale of what lies beyond Neptune become real to you, not as an abstraction but as a felt sense, a physical awareness of the emptiness and the cold and the distances involved. 400, 500, 700 astronomical units. Each astronomical unit is 150 million kilometers. Each of those hundreds of astronomical units is another 150 million kilometers further from the warmth of the Sun. The numbers are so large that they cease to be numbers in any intuitive sense and become instead a kind of poetry of distance, a way of gesturing at something that cannot truly be grasped but can be felt, at least faintly, in the body. And somewhere in that vast cold dark, if the mathematics is right, there is a world 10 times the mass of the Earth. Ancient. Silent. Alone. Waiting. We will go looking for it together tonight. And whether we find it or whether the mystery only deepens, the journey itself, the journey to the very edge of everything we know, is worth taking. It always is. Let your eyes close if they have not already. Let your breathing find its own slow rhythm. Let the day and all its small urgencies recede, the way shore recedes when you sail out onto open water, gradually, then completely, until all that remains is the vast and quiet sea. We are just beginning. So let us begin with the orbits themselves, because this is where the story truly lives, not in the imagination of any single scientist, not in the hopeful reach of a telescope pointed into the dark, but in the cold and precise language of mathematics, in the shapes that distant worlds trace through space over thousands and millions of years, shapes that should, if the outer solar system were simply empty and undisturbed, point in every direction equally, randomly, the way compass needles would if they had no north to seek. Picture for a moment what an orbit looks like, not as a circle or even an ellipse drawn neatly on a page, but as something three-dimensional, something tilted and stretched and oriented in space like a hoop that someone has thrown at an odd angle and left hanging in the void. Every object in the solar system has an orbit with a particular orientation, a particular tilt, a particular direction in which it swings closest to the Sun and then retreats to its farthest point. These orientations are described by astronomers using a set of numbers, a kind of coordinate language for the shape and attitude of a path through space. And for the innermost planets, for Mercury and Venus and Earth and Mars, these orientations are not random, they are shaped and nudged by the gravitational presence of Jupiter, by the slow accumulated whisper of mutual influence over billions of years. But out beyond Neptune, far beyond the reach of even Jupiter's great gravity, in the realm of the extreme trans-Neptunian objects, in that cold and scattered periphery of the solar system, there is no reason, no known reason, why orbits should cluster. There is no reason why they should all point in the same direction, like flowers all turning their faces toward a light source that no one can see. And yet, they do. Or at least, the ones we had measured by 2016 did. 6 of them, small icy worlds drifting far beyond the reach of ordinary planetary influence, all having their closest approach to the Sun, their perihelion, grouped in the same general direction of space. All tilted at similar angles. All oriented, in the technical vocabulary of orbital mechanics, in a way that defied the expectation of randomness. Konstantin Batygin, a young planetary scientist then at Caltech, and Mike Brown, his colleague and collaborator, looked at these 6 objects and asked the question that every scientist must ask when confronted with a pattern: is this real, or is it coincidence? Is the universe actually trying to tell us something, or are we, as pattern-hungry human minds so often do, finding meaning in noise? The mathematics gave them an answer, and the answer was striking. If the outer solar system were empty, if nothing were shaping those orbits, if chance alone governed where these icy wanderers pointed their elongated paths, then the probability of seeing 6 objects clustered the way these 6 were clustered was roughly 1 in 14,000. Written as a percentage, that is approximately 0.007%. Not impossible, but vanishingly unlikely, the kind of number that, in science, raises the serious question of whether something is being left out of the equation. Think of it this way: imagine you have a great spinning wheel, the kind used in old games of chance, divided not into numbered wedges but into all the possible directions that an orbit might point, a full 360 degrees of possibility. Now imagine that 6 separate people each spin the wheel independently, and every single one of them lands on the same narrow wedge, or very close to it. You might, if you were generous, say that it happened by chance. But you would be forgiven for suspecting that the wheel had been weighted. That something invisible had biased the outcome. That there was, in the language of orbital mechanics, a shepherd. The word shepherd is not merely poetic, though it carries a certain quiet beauty in this context. In planetary science, a shepherd is a gravitational influence, typically a moon or a planet, that corrals other objects into a particular configuration, that prevents them from spreading into randomness, that keeps them, through the repeated gentle push and pull of gravity over long timescales, organized around a particular geometry. Saturn's rings, those breathtaking bands of ice and rock, are partly maintained by small shepherd moons that patrol their edges, that nudge stray particles back into line. Gravity, in this sense, is a kind of patient and invisible herder. And what Batygin and Brown proposed was that the clustering of these 6 extreme Kuiper Belt objects, their inexplicable tendency to all point their orbital elongations in the same direction, their similar tilts, their aligned perihelia, all of it was the signature of a shepherd, a very large, very distant shepherd, one that had been exerting its influence over these icy worlds for billions of years, so slowly that we never noticed, but so consistently that the pattern had been pressed into the fabric of their orbits like a fingerprint. Let the image settle for a moment, a world far beyond Neptune, beyond the scattered disk, beyond anything we have yet visited or even seen clearly, slowly and ceaselessly organizing the smaller bodies around it, leaving its gravitational signature written in their paths the way wind leaves its signature in the shape of dunes. The perihelion alignment is perhaps the most striking component of this signature. Perihelion, you may remember, is the point in an elliptical orbit where an object swings closest to the Sun, the bottom of the arc, so to speak, before the long retreat back into darkness. For a random distribution of objects in the outer solar system, perihelia should point in all directions with no preference. But these 6 objects had their perihelia clustered together in physical space, all diving closest to the Sun in approximately the same direction, then retreating together in the opposite direction, toward the same far, cold region of the sky. Batygin and Brown ran simulations. They populated a model outer solar system with test particles, with mathematical stand-ins for small icy bodies, and they introduced a distant, massive object moving along a specific type of orbit. And what they found was that over hundreds of millions of years, the gravitational influence of this distant body would naturally produce exactly this kind of clustering. It would shepherd the smaller objects into anti-alignment with its own orbit, meaning the small bodies would tend to have their perihelia pointing opposite to where the large body's perihelion was pointing. Like 2 dancers on opposite sides of a revolving floor, always facing away from each other but always in the same relationship. And then there were the anti-aligned objects themselves. It's a smaller but equally compelling subset of extreme trans-Neptunian bodies whose orbits pointed not in the same direction as the main cluster, but in precisely the opposite direction. Perpendicular to the main cluster, or tilted at extreme angles. Objects that seem to orbit the Sun in a plane dramatically inclined relative to the flat disk of the solar system, tilted by 30 degrees, by 50 degrees, by even greater angles. These objects, too, seem too numerous and too oddly aligned to be accidental. And here is where the mathematics became particularly elegant, because when Batygin and Brown added the hypothetical planet to their simulations, they found that it did not merely explain the main clustering. It also naturally produced these high-inclination, anti-aligned objects as a secondary effect. The gravity of the distant shepherd would occasionally capture small bodies in unusual resonance configurations, flinging them into inclined orbits that would then precess, over millions of years, around to the opposite side. The unusual objects were not exceptions to the Planet 9 hypothesis, they were additional predictions of it. Like a theory of chemistry that explains not just one reaction but correctly predicts the products of half a dozen others. This is what mathematicians and scientists mean when they speak of explanatory power. It is not enough for a hypothesis to explain the one thing that prompted it. The truly compelling hypothesis explains several things simultaneously, and predicts others that had not been observed when the hypothesis was first proposed. Planet 9's proposed orbit did exactly that. It explained the main clustering. It explained the anti-aligned objects. It predicted that roughly the same percentage of newly discovered extreme Kuiper Belt objects would continue to show this clustering. And it gave the observers a target, a region of the sky, an approximate distance, a range of orbital parameters within which the planet, if it existed, was most likely to be found. So now close your eyes a little more fully, let the darkness behind them be not empty but full of slowly moving worlds, full of orbits as patient as geological time, and ask with me the natural question that follows. If the mathematics point so clearly toward a world out there, if the gravitational fingerprint is so legible in the orbits of these smaller bodies, if the simulations reproduce the pattern with such fidelity, then why, a decade later, have we still not found it? The answer to that question is a story about darkness and distance and the particular cruelty of the cosmos when it comes to hiding things in plain sight. At 500 astronomical units from the Sun, light is a memory. Not an absence, exactly, but so attenuated, so thinned by the vast geometry of distance, that it barely deserves the name. 1 astronomical unit is the distance from the Earth to the Sun, roughly 93 million miles, a number large enough to be meaningless without a reference. At 500 astronomical units, you are 500 times the distance from the Sun. You are 46.5 billion miles from the nearest star. The Sun, seen from that vantage point, would be merely the brightest star in the sky, not the overwhelming furnace we know from Earth, not the source of warmth and seasons and life, but simply a very bright point of light, cool white against the black, flanked by other stars, indistinguishable in kind if not entirely in degree. And here is the crucial consequence of the distance for the question of detection. Objects in our solar system are visible to us because they reflect sunlight. The Moon, Mars, Jupiter, every planet and asteroid and comet we can see in the night sky shines with borrowed light, with photons that originated in the Sun's nuclear furnace, traveled outward, struck a surface, and bounced back to our waiting eyes or instruments. The brightness of a reflective object depends on two distances, the distance from the Sun to the object, and the distance from the object to the observer. The relationship is not linear but follows what astronomers call an inverse square law, meaning that if you double the distance, the brightness does not halve, it drops to 1/4. And if you quadruple the distance, brightness drops to 1/16. At 500 astronomical units, Planet 9, if it exists, receives 250,000 times less sunlight than the Earth does. Even if it reflects that light with perfect efficiency, which no real body does, it would appear to us incredibly faint. In practice, with a reasonable estimate of its reflectivity, Planet 9 at 500 AU would shine at roughly magnitude 22 or fainter in the sky. To put that number in perspective, the human eye can see objects down to about magnitude 6 on a very dark night. A modest backyard telescope might reach magnitude 13 or 14. The famous Sloan Digital Sky Survey, one of the most comprehensive sky surveys ever completed, reached down to about magnitude 22 in some configurations. We are talking about an object that even our best existing surveys could barely brush against in sensitivity, that would appear in an image, if it appeared at all, as a single faint speck almost indistinguishable from the thousands of background galaxies and stars populating every square degree of sky. And it moves so slowly. This is the other great challenge, the one that makes the hunt uniquely difficult. When astronomers search for moving objects in the solar system, they typically take multiple images of the same patch of sky separated by hours or days or weeks, and then look for the telltale shift, the small displacement of a point source against the fixed background of stars. Asteroids in the main belt move perceptibly over hours. Even Pluto, at 40 astronomical units, moves enough across the sky over days that its discovery in 1930 was possible with the photographic techniques of that era. But Planet 9, at 500 to 700 astronomical units, moves with almost geological patience. Its orbital period around the Sun would be somewhere between 10,000 and 20,000 years. Over the course of a single year, it would creep across the sky by perhaps a fraction of an arcsecond. An arcsecond, to give you a sense of the scale, is 1/3600th of a degree. The full moon spans about 1800 arcseconds. A human hair held at arm's length spans roughly 100 arcseconds. Planet 9, over the course of a year, might shift by less than 1 arcsecond against the background stars, and over the course of a night, it would be effectively stationary. This is not merely inconvenient. It means that the standard search techniques, the blink comparator method that found Pluto, the automated moving object detection algorithms that have found thousands of asteroids, work poorly or not at all at these distances. The motion is so slow that it blends into the noise of the images themselves, into the tiny positional errors introduced by atmospheric turbulence and imperfect instrument calibration. Finding Planet 9 requires not just sensitivity, not just the ability to detect a faint point of light, but extraordinary precision in measuring the positions of countless faint sources across multiple observations separated sometimes by years. And then there is the sky itself, or rather, one particular region of it. The Milky Way's galactic plane stretches across the sky as a dense, creamy band of stars, packed so closely in angular terms that in some directions there are millions of stars visible in a single degree of sky. This dense star field is not merely visually overwhelming. It is observationally paralyzing for the purpose of finding Planet 9. Because against that crowded background, a single faint moving point becomes nearly impossible to isolate. Every attempt to subtract the background and look for faint objects is confounded by the sheer density of the star field, by the overlapping halos of neighboring stars, by the noise that complexity introduces into an already difficult measurement. Some of the orbital models for Planet 9's predicted position place it uncomfortably close to the galactic plane for at least part of its orbit. If the planet is currently in that region of the sky, and it well might be, then it would be, for all practical purposes, hidden not by darkness but by excess light, buried under an avalanche of stars, impossible to distinguish with current technology. The search campaigns have been many and serious and dedicated, and each one has come home from the dark with empty hands, or nearly so. Mike Brown and his collaborators, the very people who predicted Planet 9's existence, have been among the most tireless in searching for it. Using the Subaru telescope in Hawaii, one of the largest single-mirror telescopes in the world with an 8.2-meter primary mirror and a wide-field camera called HyperSuprimecam, they have surveyed large swaths of sky in the region where their orbital modeling suggests Planet 9 is most likely to be found. The HyperSuprimecam is a remarkable instrument, capable of imaging a region of sky larger than 9 full moons in a single exposure, reaching depths of magnitude 26 and beyond. And yet the survey has so far returned nothing, no candidate at the predicted distance, no slowly moving faint point that cannot be explained as something closer or more mundane. Scott Shepard and Chad Trujillo, who were themselves involved in some of the early discoveries of extreme trans-Neptunian objects, have conducted their own dedicated search programs using telescopes in Chile and Hawaii. They have found new extreme Kuiper Belt objects with every observing season, objects that have in some cases added to the statistical case for Planet 9's existence, that have fallen into the predicted clustering with an almost maddening regularity. But the planet itself has remained elusive. The Outer Solar System Origin Survey, known by its acronym OSOS, undertook a particularly careful and methodologically rigorous search for extreme trans-Neptunian objects using the Canada-France-Hawaii telescope, and their results complicated the picture somewhat. The OSOS team was meticulous about characterizing their survey's detection biases, about understanding exactly which parts of the sky they had looked at and how thoroughly they had looked. And when they corrected for those biases, some of the apparent clustering of extreme trans-Neptunian objects became less statistically significant. Not absent, but less overwhelming. Their findings did not disprove Planet 9's existence, but they introduced a note of caution into the conversation, a reminder that in science the appearance of a pattern and the reality of a pattern are not always the same thing. Dedicated machine learning searches through the archives of old sky surveys have added another chapter to the hunt. Teams of astronomers have written algorithms to comb through the enormous data sets of past sky surveys, looking for faint moving objects that human eyes might have missed, for the slow drift of a distant world preserved in photographic plates taken decades apart. These archival searches have found new trans-Neptunian objects, have extended the known population of distant solar system bodies, have helped refine the statistical analysis. But Planet 9 itself has not emerged from these archives, not yet. And then there is the Atacama Cosmology Telescope and other microwave surveys of the sky, which were never designed to search for planets but which contain, in principle, the thermal signature of any object warm enough to emit in their wavelength range. Planet 9, at the distances predicted, would be extremely cold, perhaps 50 to 60 degrees above absolute zero, but it would still emit faint thermal radiation that might, in principle, show up in these datasets. Careful analyses of Atacama Cosmology Telescope data and Planck satellite maps have been conducted with Planet 9 in mind. A few intriguing candidate signals have appeared in these analyses over the years, points in the sky with the right kind of faint thermal signature, positioned not impossibly far from the predicted orbital region. But none have been confirmed. None have been seen to move as they would need to, slowly but measurably, to be ruled in as a genuine solar system object. The WISE satellite, NASA's Wide Field Infrared Survey Explorer, completed an all-sky survey in the infrared that should, in principle, have been capable of detecting a relatively warm or large planet somewhere in the outer solar system. WISE and its successor NEOWISE catalogued hundreds of millions of infrared sources across the entire sky, and searches through this catalogue have been performed specifically with Planet 9 in mind. The conclusion from most of these analyses is that if Planet 9 exists at the warmer end of the predicted temperature range, at distances closer to 500 AU or less, it would likely have shown up in WISE data by now. The fact that it has not appeared has pushed the most probable location toward greater distances and cooler temperatures, not ruling it out, but reshaping the probability map of where in the sky and how faint it might be. There is something quietly humbling about this ongoing silence, this sustained absence of the thing we are looking for. In science, as in life, the absence of evidence is not the same as evidence of absence, and yet the absence accumulates weight over time. Each negative search result does not destroy the hypothesis, but it does constrain it, pushes the planet into smaller and smaller regions of orbital phase space, demands that if it exists it be fainter or more distant or more unfortunately placed than the most optimistic predictions allowed. What the search campaigns have collectively taught us is not that Planet 9 is not there, but rather how extraordinarily well hidden it is, how perfectly the outer solar system has conspired, through distance and darkness and the accident of galactic geometry, to keep this secret. It is a reminder that the universe is not obligated to make its contents easy to find, that the final frontier in planetary science might require not just better telescopes but better patience, better algorithms, better luck, and perhaps instruments that have not yet been built. And there is one instrument, or rather one set of instruments, that represents the best hope in the present moment, the Vera Rubin Observatory in Chile, which will complete its legacy survey of space and time over the coming years, mapping the entire southern sky repeatedly in 6 different color filters, building up over time a cumulative sensitivity and aerial coverage that surpasses anything attempted before. The Rubin Observatory, with its 8.4-meter mirror and its 3.2 gigapixel camera, the largest digital camera ever built for astronomical purposes, will survey the available sky every few nights, building up a time-lapse movie of the cosmos that will reveal faint moving objects through the accumulation of many repeated observations. The combination of depth and cadence and sky coverage represents a genuinely new capability, and if Planet 9 is anywhere in the southern sky and not hidden behind the galactic plane, the Rubin Observatory should, over the course of its survey, have a realistic chance of finding it, or of constraining its existence so severely that the hypothesis itself will need to change. And alongside Rubin, there is the James Webb Space Telescope itself, which brought us here tonight, which was first mentioned in the mystery we are exploring, and which has contributed new data to this search in ways that are only now being understood and interpreted. But that story, the most recent chapter, the 2026 data, the new findings that deepen rather than resolve the uncertainty, that story belongs to a later part of our journey tonight. For now, let the image of the search itself carry you. Teams of astronomers at their computers, scrolling through images of sky so dense with stars that each frame looks like salt spilled on black velvet. Algorithms running through the night on servers in cool, humming data centers, comparing positions of faint sources across images taken days or years apart, looking for the one slow drift that would change everything. Telescopes on mountaintops turning their enormous eyes to particular patches of sky, gathering photons that have traveled from the sun, bounced off ice and rock at inconceivable distance, and traveled back across billions of miles to fall, a few at a time, onto a detector the size of a dinner table. It is a kind of patient, collective vigil. A watching and a waiting. The universe holds its secret, and we hold our instruments, and between us there is the dark, and the distance, and the slow accumulation of data that may, one day, resolve the mystery. Or it may not. And that possibility, that the mystery might not resolve in the way we expect, that the mathematics might be pointing us toward something stranger and more surprising than a planet, is where the story turns next. But first, let the silence of the outer solar system settle around you for a moment. The darkness beyond Neptune is not empty, even if it appears that way. It is full of ancient ice, full of slow orbits, full of the patient arithmetic of gravity. And somewhere in that arithmetic, something is writing its signature in the paths of smaller worlds, insisting on its own existence through the eloquence of mathematics even as it refuses to show us its face. That insistence, that hidden presence announcing itself only through the distortion it leaves behind in other things, is one of the oldest stories in astronomy. It is how Neptune itself was found in 1846, not by pointing a telescope at random but by following the mathematics of Uranus's disturbed orbit to its source. It is how the existence of black holes was accepted long before we had direct images of them, through the behavior of gas and stars in their vicinity, through the ripples they left in the fabric of space-time. The cosmos has a long habit of being found through its effects before it is found directly. And perhaps, in the dark and the cold and the patience of scientific time, Planet 9 will be found the same way. Let your breathing slow a little more. Let the images behind your eyes soften. The search continues tonight, as it has every night for years, as it will continue tomorrow and the night after that. You do not need to carry the urgency of that search right now. It is being carried, gently and carefully, by the astronomers and their instruments and their mathematics. Your only task in this moment is to rest, to let the story wash over you like starlight, cool and faint and traveling from unimaginable distances to reach you here. We have looked at the mathematics. We have followed the search. And now, quietly, we turn toward the stranger and more unsettling possibilities, the alternatives that science must always hold open, that honest inquiry always keeps on the table. What if it is not a planet at all? What if the thing leaving those orbital fingerprints is something even more improbable, even more extraordinary? What if it is a black hole? That question, and all the other competing hypotheses that rigorous science demands we consider, wait for us just ahead, resting in the dark, as patient as everything else at the edge of the solar system, asking to be looked at clearly, with neither fear nor false certainty, but with the open and rested mind that only the quiet of a night like this can bring. Let the darkness be comfortable. Let the questions be gentle. There is no rush. The universe has waited for 0.6 billion years to reveal this secret, and it will wait a little longer while you rest. We are sailing now past the known edge, past the last mapped territories, past the final outposts of the familiar. And there is a kind of peace in that, a kind of permission that the outer solar system grants, permission to not know, permission to wonder without resolution, permission to let the mystery be exactly what it is, vast and cold and patient and beautiful in its refusal to yield easily to our questions. Let your body settle a little more deeply into wherever you are resting. Feel the weight of yourself, the quiet miracle of a body at rest, held gently by gravity, warmed by its own slow processes, breathing without effort. You are here. The mystery is out there. And the distance between you and it, that impossible distance, is not a source of anxiety but of comfort, a reminder that some questions are larger than any single night, larger than any single life, and that their largeness is not a burden but a gift. We are just beginning to understand what lies at the edge of everything we know. And that beginning, that first careful reaching toward the unknown, is enough for tonight. So let us drift a little further now, not with urgency, not with the sharp focus of a scientist at a telescope, but with the soft and wondering attention of someone who has already learned enough for one evening and is now simply allowing the mind to move where it wishes, following the gentle current of thought toward stillness. We have traveled together through so much tonight. We have stood at the edge of the solar system and looked outward into the dark. We have followed the mathematics of two astronomers as they traced impossible orbital patterns and arrived, with trembling certainty, at the conclusion that something vast and unseen must be shaping the architecture of the outer worlds. We have felt the frustration of a decade of searching, the telescope lenses swept across billions of stars, the algorithms sifting light from light, finding nothing, and yet the absence itself forming a kind of shape, the way silence in music is still part of the music. And now we arrive at the question that contains all the others. Not merely what is out there, but what it would mean, for all of us, for our understanding of everything, if we are simply wrong about our own solar system. If the place we call home, the gravitational family we were born into, has been hiding something from us all along. This is not a question with an easy answer. It is not even a question with a clean shape. It spreads outward in all directions like rings on water, touching everything we thought we understood and asking quietly whether we understood it at all. Begin with the solar system formation models. These are the stories we tell ourselves about where we came from, the careful reconstructions built from physics and chemistry and the study of distant star systems. For decades, the standard model of solar system formation has been elegant in its simplicity. A disk of gas and dust surrounds a young star. Gravity pulls material together. Small bodies collide and merge. Planets grow from these collisions, their orbits settling into stable configurations over millions of years. The gas giants, Jupiter and Saturn and Uranus and Neptune, form in the outer regions where temperatures are cold enough for ice to exist, giving them abundant building material. The rocky planets form in the warmer inner regions. And after a few 100 million years of turbulence and reshaping, the solar system settles into something resembling what we see today. It is a beautiful story. And it fits the evidence remarkably well, for most of the solar system. But Planet 9, if it exists, is a problem for this story. A significant and perhaps fundamental problem. Because a planet of 10 Earth masses does not simply drift to 500 astronomical units on its own. Nothing in the standard formation model places a super-Earth at such extreme distances. The disk of material from which planets form did not extend that far out. There was not enough material at those distances to build anything close to 10 Earth masses. The timescales would not have permitted it. A body trying to grow by accretion at 500 AU would find its building blocks too sparse, too slow, the collisions too infrequent, the orbit too vast for enough encounters to occur before the disk dissipated. So if Planet 9 is out there, it did not form there. It formed somewhere else. And something moved it. This is where the story becomes genuinely strange, genuinely interesting, and genuinely unsettling in the most wonderful way. Because the mechanisms that could move a super-Earth to the outer solar system are not gentle. They involve catastrophic gravitational interactions between the young planets, close encounters that would have reshaped the entire architecture of the inner system, the kind of chaotic early solar system that leaves scars we might be able to read if we know where to look. One possibility is that Planet 9 formed in the region between Jupiter and Neptune, roughly where Uranus and Neptune themselves formed. In the turbulent early period when the giant planets were still migrating, still finding their final orbits, a gravitational encounter with one of the larger giants could have flung a smaller planet outward. Not destroyed it, not ejected it entirely from the solar system, but placed it on an enormously elongated orbit that carries it out to hundreds of astronomical units and brings it back close enough to still exert gravitational influence. A slow, elliptical path, measured in thousands of years per orbit. A prisoner of the solar system, but one confined to a cell so vast that we have never been able to see it. The NICE model, one of the most influential frameworks for understanding the early solar system, already proposes a period of dramatic migration among the giant planets. In this model, Jupiter and Saturn crossed a gravitational resonance that sent Neptune and Uranus scattering outward, and in the process flung enormous numbers of smaller bodies throughout the solar system and beyond. The late heavy bombardment, that era roughly 4 billion years ago when the inner solar system was pelted with impacts, may have been a direct consequence of this giant planet migration. The craters on the Moon that you can see with the naked eye on a clear night, those ancient wounds in the lunar surface, may be echoes of this early chaos. Planet 9 would fit naturally into this picture as one more casualty of the early migration period. A world that grew too large in the wrong place, caught by the gravitational wake of a passing giant planet, and sent on its lonely journey to the outermost reaches of the solar system, where it has drifted ever since, in darkness and cold and silence, while on a small warm planet 8 light-hours away, creatures who came from the same original cloud of dust eventually developed mathematics and telescopes and learned to ask questions about where they came from. There is something deeply moving about that story. Not just scientifically but in a human sense. We and Planet 9, if it exists, are siblings. Children of the same stellar nursery, shaped by the same forces, participants in the same ancient drama of gravity and time. And we have never met. But now consider what happens if Planet 9 does not exist. If the orbital clustering that Batygin and Brown observed is indeed an artifact of how we look rather than a signal of what is there. If the surveys that discovered the clustered extreme trans-Neptunian objects were all conducted in the same region of sky, and the clustering reflects not the gravitational influence of a hidden world but simply the area where telescopes were pointed. This is the observational bias argument, and it is not a fringe position. It is a serious scientific challenge raised by careful researchers who have spent years examining the data. In 2019, a study led by Kevin Napier at the University of Michigan analyzed the existing surveys of extreme trans-Neptunian objects and concluded that when you account for the biases inherent in where different surveys looked, the statistical significance of the clustering largely disappears. Not entirely. The debate continues, as all good scientific debates do. But the possibility that we have been chasing a ghost, that the clustering is a pattern we imposed on the data rather than a pattern the universe placed there, is one that responsible science cannot dismiss. And if that is the case, then what? Then we are left with a Kuiper Belt and scattered disk that behave roughly as expected. Then our formation models are fine, our understanding of the outer solar system is approximately correct, and the apparent anomaly was an artifact of incomplete observation. This would be a kind of anticlimax, perhaps. The mystery dissolved not by discovery but by the realization that there was no mystery after all. But even this resolution carries its own kind of lesson, its own kind of wonder. Because what it would tell us is how extraordinarily difficult it is to see the outer solar system clearly. How our instruments and our methods and our very humanity, our tendency to point telescopes at the most promising areas of sky, inevitably shapes what we find. It would be a lesson in epistemic humility, in the importance of examining not just the universe but the tools and assumptions we bring to that examination. The philosopher of science Karl Popper wrote that the goal of science is not to find certainty but to eliminate error, to test ideas against reality and discard the ones that fail. In that framework, either outcome here is a success. Either Planet 9 is confirmed and we learn something astonishing about our solar system's history and structure. Or Planet 9 is disproven and we learn something equally important about how science goes wrong and how it corrects itself. Both are victories of a kind. Both add something real to the sum of human understanding. Compare our solar system to the thousands of others we have now discovered, and the perspective shifts again. In exoplanet surveys, the most common type of planet found around other stars is something that does not exist in our solar system at all. The super-Earth, a rocky or partly rocky planet with a mass between 1 and 10 times Earth's, is extraordinarily abundant in the galaxy. Nearly every other star system seems to have at least one. They are arguably the universe's favorite kind of planet. And yet our solar system has none. Between Earth at 1 Earth mass and Neptune at 17 Earth masses, there is nothing. A strange gap. A conspicuous absence. The planet masses in our solar system skip over the most common size in the universe. Some researchers have proposed that our solar system did once have super-Earths, in the inner regions between Mars and Jupiter, but that they were destroyed in the early period of giant planet migration. Swept up, flung out, consumed. A planetary genocide in the early solar system that cleared the inner regions and may have been a prerequisite for the stability that allowed Earth to develop life over billions of years. If Planet 9 is real, it may be the last survivor of that purge. A super-Earth that escaped the inner massacre by being thrown outward rather than inward. Living out an extremely eccentric, extremely distant existence as the sole representative of a class of planet that should have been our neighbors but instead became our most distant and invisible relative. And what would confirmation mean, practically? What would it mean for the story of where we came from, for the way we understand ourselves in the cosmos? It would mean that our solar system is stranger than we thought. More violent in its past, more complex in its structure, more alive with hidden forces than the orderly elliptical orbits visible through even a modest backyard telescope would suggest. It would mean that the quiet, apparently stable system of planets we inhabit is built on a history of chaos and coincidence, and that our existence here, on this warm, rocky world, is the outcome of a sequence of improbable events that could easily have gone otherwise. There is humility in that. And there is also a strange kind of grandeur. Because it means that the solar system is not a simple mechanism that a clever enough mind could derive from first principles. It is a particular, contingent thing. It happened this way, and it might have happened any number of other ways, and the fact that it happened in a way that eventually produced beings capable of wondering about it is something. Something worth sitting with. Something worth feeling, quietly, at the end of a long day, as the mind begins to soften towards sleep. And now let the science rest for a moment, let the data and the debates and the statistical arguments settle slowly, like dust in still air. Let them take their places in the back of the mind where they will continue their slow, quiet work without needing your attention. Because now we drift. We go outward. Not in a spacecraft, not with instruments or calculations, but with the imagination alone, that oldest and most faithful of telescopes. Begin at Neptune. Stand for a moment, in your mind's eye, at a distance where this blue world fills a portion of the sky. Not the brilliant blue of Earth as seen from space, full of cloud and ocean and light. Neptune is a deeper blue, a darker blue, the blue of something very cold and very far from warmth. At this distance, the Sun is a bright star, brighter than any star in our sky, but recognizably a star, a point of light rather than a blazing disk. It gives heat that you would not be able to feel. It gives light, but not enough to read by. Not enough to cast sharp shadows. Just enough to faintly illuminate the clouds that swirl in Neptune's atmosphere, those enormous storms larger than continents, moving through methane and hydrogen and helium in silence. Neptune has moons. Triton, the largest, is a world of nitrogen ice and frozen plains, with geysers that vent dark plumes into its tenuous atmosphere. It orbits Neptune backwards, which tells us that it did not form alongside the planet but was captured from the outer solar system long ago, pulled in by Neptune's gravity and set on its retrograde path, slowly spiraling inward over billions of years. In a distant future, far beyond any human timescale, Triton will come close enough to Neptune that tidal forces will shatter it, and Neptune will have a ring system for a while, before that too disperses. Everything is process. Everything is in motion. Even the things that seem most permanent and still are engaged in their slow trajectories toward transformation. Move outward past Neptune. The gas giant falls behind you. Its blue light diminishes. Ahead, the Kuiper Belt begins. The space does not announce itself with any visible boundary. You simply find that there are more objects here than you have been accustomed to. Not many more, by any everyday measure. Even the densest part of the Kuiper Belt is extraordinarily empty by human standards. If you were in a spacecraft, you could travel through it for years without coming close to any single object. But compared to the void beyond Neptune, the Kuiper Belt is busy, populated, alive with small cold worlds going about their ancient orbits. Some of them are large enough to be seen, in your imagination, as you drift past. Pluto, perhaps most famous, a world of nitrogen ice and mountains of water ice, with a heart-shaped plain called Tombaugh Regio that is bright enough to be visible from a great distance. Its surface is young in geological terms, reshaped by processes that are still not fully understood. Nitrogen ice glacier flow slowly across its surface, filling craters and erasing old features. Pluto is not the dead, static ice ball we once imagined, but something more active, more complex, more interesting. Arrokoth, the small contact binary visited by New Horizons in 2019, drifts somewhere in this region too. Its two lobes, which the team nicknamed Ultima and Thule before settling on the Powhatan word Arrokoth meaning sky in the language of the people of that land, came together slowly, at walking speed, two bodies that formed in the same region and gradually merged over millions of years. It is a primitive thing. Ancient. Shaped by forces that were active in the first few million years of the solar system's existence. Looking at Arrokoth is like looking at a piece of the original cloud of material that became everything. Float here for a moment. Let the silence settle around you. There is no sound, of course. Space carries no sound. But silence is not merely the absence of noise. It has a texture. The silence out here would feel different from the silence of a room. Deeper. More absolute. The kind of silence that is not waiting for something to happen but simply is, in itself, complete. The sun is smaller now. Noticeably smaller. Its light is dimmer. If you were to hold up your hand in this light, you would barely see it. The warmth of the sun, which on Earth we take for granted, which we feel every time we step outside, has become a memory out here. A theoretical quantity. The temperature in the space through which you drift is roughly minus 240 degrees Celsius. Close to absolute zero. Close to the coldest temperature the universe permits, that theoretical floor below which nothing can go, the temperature at which all thermal motion would cease. And yet even here, even in this cold, objects move. They drift in their orbits with the patient persistence of things that have been doing this for 4.5 billion years and see no reason to stop. The frozen worlds of the Kuiper Belt do not experience time the way living things do. They simply exist. They move because gravity requires it. They change so slowly that billions of years pass like a quiet afternoon. Further out now. The Kuiper Belt thins behind you. Ahead, the scattered disk begins. This is the region where the most extreme trans-Neptunian objects live, those objects whose orbits were distorted by close encounters with Neptune long ago, sent on eccentric paths that carry them far from the Sun and bring them back in cycles measured in thousands of years. Sedna, perhaps the most famous of these worlds, lives here, or rather its orbit passes through here. Its closest approach to the Sun is still more than 76 AU away. It never comes close enough for Neptune's gravity to influence it significantly, which is part of what makes it so strange, and why it has been suggested as one of the objects that might be under the gravitational influence of something much more distant. Sedna is red. Deep reddish-orange, the color produced by long exposure to cosmic radiation acting on carbon-bearing ice, producing complex organic molecules called tholins that coat the surface. It is ancient and red and lonely, drifting on its enormously elongated path. Its full orbit takes 11,000 years. In 11,000 years of human history, we went from small scattered populations using stone tools to a civilization that builds space telescopes and discovers worlds like Sedna itself. And in that same time, Sedna barely moved. Let your speed increase a little in the imagination. Let the scattered disk pass below you, its sparse population of ancient bodies drifting in the deep cold. The Sun has become a bright star. A very bright star, yes, the brightest in the sky, but no longer a sun in any felt sense. No longer a source of warmth or light that you could use to see by. Just a star. The brightest star. And around it, if you know where to look, you can trace the orbits of the planets, those barely perceptible points of light moving almost imperceptibly against the background of all the other stars. And out here, somewhere, perhaps somewhere near where you are drifting right now, there may be another world. Cold and dark and vast. Larger than Earth. Smaller than Neptune. Orbiting so slowly that in an entire human lifetime it moves only a fraction of a degree along its path. If it exists, it glows only faintly with reflected sunlight, that sunlight now so weak at this distance that even the enormous eye of a space telescope might mistake it for a distant galaxy or miss it entirely against the brightness of the Milky Way. If it exists. Hang there in the dark for a moment, in the imagination, and simply hold that possibility. Not as a fact. Not as a certainty. As a possibility. The universe is under no obligation to be fully mapped or fully known in any particular century. The edge of human knowledge is always, by definition, the edge of darkness. Beyond what we can see lies what we cannot see yet. And beyond that lies more. There is no shame in not knowing. There is no failure in uncertainty. The most important thing that science has ever taught us is not any particular fact but the practice of holding ideas with exactly the right amount of grip. Tight enough to act on them, to build experiments and predictions from them. loose enough to let them go when the evidence demands it. This is not weakness. It is the most rigorous form of honesty there is. You float in the dark beyond the scattered disk, and somewhere in the black surrounding you, photons are moving. They have been moving for 8.5 minutes from the sun, or for hours, or for years, and they travel in all directions, carrying the sun's light outward into space. Most of them will travel forever, growing ever more diffuse, never hitting anything, carrying their tiny parcels of energy across the galaxy and eventually the universe until the universe itself is old enough and dark enough that they simply continue. In the dark. Among the dark. Unobserved and unobserving. Some of them, tonight, are hitting the sensors of the James Webb Space Telescope, or the Vera Rubin Observatory, or the Subaru telescope on the summit of Mauna Kea. And in those sensors, those remarkable human-made instruments built by thousands of people over decades, those photons are being converted into information, into data, into numbers that will be examined by minds and algorithms, looking for the signal in the noise. Looking for the thing that should not be there, that statistically cannot be absent, that the mathematics of gravity insists must exist somewhere in this dark. They are still looking. The search did not end tonight. It will not end tomorrow. It may be years yet before we find what we are looking for, or before we confirm, with sufficient evidence, that there is nothing to find. The universe does not hurry. The mystery does not resolve on a schedule convenient for the humans asking the question. And that is all right. That is more than all right. That is how it should be. Because the mystery is not a problem to be solved and then set aside. The mystery is a relationship. It is the ongoing conversation between human curiosity and the universe's depth, and like all the best relationships, it does not have a destination so much as a direction. A leaning toward. A willingness to keep asking even when the answers take a long time, even when the answers do not come at all, even when the answers lead to new and stranger questions. We have been asking questions about the night sky for as long as we have been human. We sat around fires in the dark and looked up at the stars and felt the pull of them, the desire to understand, the need to name and map and explain. We built stone circles that tracked the solstices. We carved astronomical records into clay tablets. We mapped the orbits of planets with the naked eye over centuries of careful observation. We ground glass into lenses and saw things that no human eye had ever seen before. We launched instruments into space and aimed them at objects too faint and too far for any earlier technology to reach. And we still have not reached the bottom of the sky. We still have not asked all the questions. We still do not know everything about the place we live. This is not a source of anxiety. Let it not be a source of anxiety. It is a source of wonder. It is an invitation. The universe is inexhaustible. Its depth is not threatening but generous. No matter how long we look, no matter how precisely we measure, no matter how sophisticated our instruments become, there will always be more. The edge of knowledge will always recede before us. Not because reality is hiding from us, but because reality is simply very, very large, and we are very, very small, and the gap between us and full understanding is not something to mourn but something to cherish. Let your breathing slow now. Let the thoughts that have been moving through your mind begin to settle. The science is done for tonight. The questions are still open, still alive, still drifting out there in the dark where the Kuiper Belt objects trace their patient paths. But your engagement with them can rest. The mind does not need to keep turning over the details. The orbit of Planet 9, if it is real, will still be there tomorrow. The data from the James Webb Space Telescope will still be there tomorrow. The questions will still be worth asking tomorrow. But tonight, the mind can release them. Tonight, the mind can drift. Think, if you wish, of the cold. Not an unpleasant cold, but the vast, clean cold of deep space. The temperature of the cosmos, far from any star, is a number so close to absolute zero that it almost has no temperature at all. Almost no motion in the molecules. Almost no vibration. A stillness so profound that our instruments can barely measure it. That stillness is not emptiness. It is presence. It is the universe resting in itself, occupying its own enormous volume with a kind of perfect equanimity. The stars burn and the planets orbit and the comets streak and the distant galaxies wheel on their vast axes, and all of this happens in a space that is primarily, overwhelmingly, peacefully, nothing. Or very nearly nothing. Quiet. Dark. Patient. Waiting. You are made of the same material as the stars. The iron in your blood was forged in the nuclear furnaces of stars that died before the sun was born. The calcium in your bones was scattered by ancient stellar explosions across light-years of space. The oxygen in your lungs, the carbon in your cells, the water in your blood, all of it came from somewhere else, from something that died so that you could live, from processes that took billions of years to complete, from distances that you cannot travel in a lifetime. You are ancient. You carry the universe's history in your body. And right now, that body is at rest. Feel the weight of it. The pleasant heaviness of a body that is done moving for the day. The slight warmth of breath. The slow, almost imperceptible rise and fall of the chest. The way the thoughts, when you stop feeding them, begin to slow of their own accord, like ripples on water when no more stones are thrown. Somewhere out beyond Neptune, beyond the Kuiper Belt, beyond the scattered disk, beyond even the region where Planet 9 might be waiting in the dark, there are the first faint hints of the Oort cloud. That enormous spherical shell of icy bodies that surrounds the entire solar system at distances of tens of thousands of astronomical units. The Oort cloud has never been directly observed. It is inferred from the comets that fall inward, those long-period comets that arrive from all directions in the sky, telling us that their origin point is a sphere, not a disk, a vast surrounding shell of material that marks the true outer boundary of the Sun's gravitational influence. The Oort cloud is so far away that it extends nearly halfway to the nearest star. It is where the solar system ends and interstellar space begins. Beyond it, the Sun's gravity is barely holding on. The objects there are only marginally bound, prone to being disturbed by passing stars, by the gravitational tides of the galaxy itself. A small nudge from anything passing by can send an Oort cloud object falling inward on a journey of 10,000 years, arriving eventually as a comet in the inner solar system, burning briefly and brilliantly before returning to the dark. Let the Oort cloud be the last image in your mind tonight. That vast, spherical, tenuous cloud of ice and dust and silence, surrounding everything, marking the edge of home, the boundary between the familiar and the truly interstellar. It is out there right now, surrounding you in all directions, an invisible sphere of ancient quiet. And inside it, inside the enormous space it defines, the planets orbit. And on one of them, you exist. You are inside the solar system. Inside the Oort cloud. Inside the Milky Way. Inside the local group of galaxies. Inside the observable universe. Nested in structure after structure, each one larger than the mind can hold, each one exquisitely indifferent to your concerns and at the same time, somehow, the context from which your concerns emerged. The thoughts are growing quieter now. That is the right direction. Follow the quiet. The mind, when it lets go, moves in gentle spirals. It does not need to go anywhere tonight. It does not need to solve anything or remember anything or plan anything. It can simply be the way an Oort cloud object is, drifting slowly in the cold, held by a gravity so gentle it might be mistaken for freedom. Your breathing is slower now. The breath goes in, cool and clean. It goes out, warm and soft. The body knows what to do. The body has been doing this for your entire life, breathing in and out in the dark, restoring itself while the mind rests. Trust the body. It knows the way. The questions about Planet 9, about the orbital clustering, about the mathematical predictions and the telescope surveys, all of it is still there, but it has moved to a different room. A quiet room, a room where things are stored safely and will still be there when you return. Nothing is lost. Everything you learn tonight is somewhere in you now, settling into place, finding where it fits, beginning the slow work of becoming part of how you see things. Science is always doing this. It is always finding its place in the larger story of what we know, adjusting and being adjusted by the things around it. And in the same way, each night, the mind finds its place in the larger structure of rest, adjusting and being adjusted by sleep, by the quiet and the dark, by the body's slow wisdom. Go there now. Follow the breath down, down, into the dark behind the eyes where thought becomes image and image becomes feeling and feeling dissolves gently into rest. There is nothing required of you now. Nothing to figure out. Nothing to hold. The mystery is out there, vast and cold and patient. And you are here, warm and small and briefly awake in a universe that has been going about its business for 14 billion years without asking anything of you. The mystery will still be there in the morning. The scientists at their telescopes will still be looking. The data will still be accumulating. The mathematical predictions will still be waiting to be tested. But that is for tomorrow. Tonight is for this. The slow, soft letting go. The breath. The dark. The quiet that is not empty but full, full in the way that space is full, not with objects but with potential, with the capacity for wonder, with the generous silence that surrounds all things and holds them together. Let the eyelids rest. Let the hands rest. Let the mind rest. Somewhere, an extreme trans-Neptunian object continues its orbit, as it has for 4 billion years, utterly indifferent to whether it has been detected, utterly unconcerned with the arguments of astronomers, simply moving in its elegant ellipse around a distant warm star. And that object, that cold and nameless thing at the edge of everything, has been there every night of your life, every night of your parents' lives, every night since before there were humans to wonder about it. Patient as stone. Patient as gravity. Patient as time itself. There is something to learn from that. Some quality to borrow, just for the night. The patience of the outer solar system. The stillness of a frozen world drifting in the dark. The equanimity of a thing that simply exists, without needing to be understood, without needing to be seen. Be, for now, like that. Breathe. And sleep.